At 0032 Universal Coordinated Time on October 26, 2025, forecasters record solar wind speeds easing from approximately 550 kilometers per second toward 400 kilometers per second, while the north-south component of the interplanetary magnetic field briefly turns south to -6 nanotesla. Ground magnetometers at high latitudes show quiet to unsettled conditions with short active intervals. A coronal mass ejection that left the Sun on October 23 is expected to arrive on October 27, followed by stronger high-speed solar wind from a positive polarity coronal hole on October 28. The most complex active regions on the visible disk are numbered 4,262 and 4,266, with newly numbered region 4,269 emerging in the southeast quadrant. Observed flare levels in the last day are low, with C-class events and only a slight chance of isolated M-class flares. Current high-latitude auroral displays are confined to the typical auroral oval and expand only during brief southward swings of the interplanetary magnetic field. If you value evidence-based space weather coverage, subscribe, give a like, and comment with your location and what you observed tonight. A coronal mass ejection launched on October 23 is forecast to reach Earth on October 27. Arrival timing remains uncertain until the interplanetary shock is detected by upstream monitors. The likely sequence is a shock arrival, a turbulent sheath region with compressed magnetic fields, and then the main ejecta whose magnetic field orientation governs storm strength. A high-speed stream from a positive polarity coronal hole is expected to increase solar wind speed further on October 28, raising the chance of recurrent substorms, even if the coronal mass ejection itself delivers only modest effects. The most important near-term driver is the magnetic field direction within the incoming ejecta and the degree of coupling it achieves with Earth's magnetic field. When the interplanetary magnetic field points south for sustained periods stronger than 10 nanotesla, energy couples efficiently into the magnetosphere. When it points north, coupling weakens and auroral activity retreats poleward. Because the south-north component cannot be known confidently until the ejecta arrives, risk bands must be framed conditionally. Auroras are an electrical current and particle precipitation phenomenon driven by interactions between the solar wind and the magnetosphere. The solar wind carries the interplanetary magnetic field, a vector with a total strength and a directional component that can tilt north or south relative to Earth's field. When the field turns south, dayside magnetic reconnection opens flux at the magnetopause and transports energy into the magnetotail. Stored energy later releases explosively as a substorm, brightening auroras and expanding the auroral oval equatorward. Solar active regions concentrate magnetic flux and can produce flares that briefly increase X-ray and extreme ultraviolet radiation, and coronal mass ejections that eject magnetized plasma clouds into interplanetary space. Coronal holes are long-lived open-field regions that emit high-speed solar wind streams. Stream interaction regions and coronal mass ejections both modify solar wind density, speed, and total magnetic field. The combination of speed, density, and field strength sets the solar wind dynamic pressure at Earth's magnetic boundary. Higher pressure compresses the magnetopause and drives stronger ground-level perturbations. The arrival of a coronal mass ejection is marked by a sudden increase in solar wind speed, density, and total magnetic field, which is interpreted as a shock. Behind the shock is a sheath region of compressed plasma with turbulent fields, often producing intermittent southward intervals that trigger substorms. The ejecta can be a magnetic cloud with a smoothly rotating magnetic field. If the rotation includes a long southward interval, geomagnetic activity intensifies. Substorms are internal magnetospheric reconfigurations that begin with growth phase stretching of the magnetotail, onset near midnight local time, and expansion phase auroral brightening and poleward motion. The recovery phase follows as the magnetosphere relaxes. Major storms are statistically associated with shocks followed by ejecta, whose southward field persists for tens of minutes to several hours. In contrast, sheaths with patchy southward intervals can produce bursts of activity without a deep ring current intensification. A small set of standard indices and solar wind parameters lets you quantify storm strength and timing in real time. The geomagnetic K-index characterizes 3-hour magnetic field fluctuations on a quasi-logarithmic scale from 0 to 9. A geomagnetic K-index of 5 corresponds to a storm threshold, 7 to strong storm levels, 8 to severe storm levels, and 9 to extreme storm levels. The disturbance storm time index measures the strength of the ring current as an hourly global value in nanotesla. Values more negative than -100 nanotesla indicate a significant storm. Values near -400 nanotesla indicate an event comparable to the strongest storms of the modern space age. The auroral electrojet index measures auroral zone current intensification from an array of high-latitude magnetometers. Rapid increases signal substorm onset and expansion. Very high auroral electrojet values often accompany strong southward magnetic fields and elevated solar wind dynamic pressure. Core solar wind parameters you should track are speed in kilometers per second, density in particles per cubic centimeter, total interplanetary magnetic field strength in nanotesla, and its north-south component in nanotesla. The dynamic pressure combines density and the square of speed to indicate how forcefully the solar wind compresses the magnetosphere. A sudden dynamic pressure jump at the shock produces a step change in ground magnetic records. Practical thresholds for tonight and the next 2 days are as follows. If solar wind speed rises above 600 kilometers per second, if density exceeds 15 particles per cubic centimeter near shock passage, if total magnetic field exceeds 15 nanotesla, and if the north-south component turns southward stronger than 10 nanotesla for longer than 30 minutes, the auroral oval expands well into the middle latitudes. If the north-south component remains northward, auroral activity remains confined to high latitudes even with elevated speed. Visibility depends on geomagnetic strength, sky darkness, and your location relative to the auroral oval. During quiet to unsettled conditions, reliable visibility is limited to high latitudes near the traditional auroral oval. During strong storms with geomagnetic K index of 7 or higher, the auroral boundary can drop into middle latitudes, and during severe storms with geomagnetic K index of 8 or higher it can reach surprisingly low latitudes. Your best predictor remains the combination of the north-south magnetic field and sustained solar wind speed. Substorms preferentially brighten around local magnetic midnight. For observers in Europe, the best window commonly falls from 21 hours to 2 hours local time. For observers in North America, adjust by longitude so that your primary effort centers on local midnight through the early morning hours. The initial shock can trigger an early evening impulse. Plan a check around the predicted arrival. You need a dark site with minimal artificial light. Moonlight washes out faint structure. If the moon is bright and high, visibility shifts toward only the brightest arcs and pillars. Favor hours after moonset or before moonrise when possible. Clouds and fog fully block visible auroras. Short breaks in cloud cover can still reveal bright bands and curtains during strong activity. If a front is passing, scan the entire sky frequently. Auroral pillars can appear in gaps for seconds to a minute. Start due north in the northern hemisphere and due south in the southern hemisphere, 20 to 40 degrees above the horizon. Then scan azimuthally across the sky. During strong events, the entire sky can fill from horizon to zenith. Use a sturdy tripod. Use a fast wide-angle lens between 14 mm and 24 mm full-frame equivalent. Set a wide aperture. Begin with an exposure of 20 seconds at high sensitivity between 3200 and 6400 and adjust by half stops based on brightness. If bright rays introduce streaking, shorten the exposure to 10 seconds. Focus manually on a distant light or a bright star and lock focus. Use a remote release or a 2-second delay. Space weather primarily affects systems that rely on long conductors or near-Earth plasma conditions, with impacts scaling with storm strength and duration. Rapidly changing magnetic fields induce currents in long transmission lines. These geomagnetically induced currents can heat transformer cores, shift reactive power, and in worst cases contribute to voltage collapse. Grid operators mitigate by switching configurations, reducing transfers, and monitoring harmonics. Standards bodies have codified planning practices to assess benchmark geomagnetic disturbance events and to harden assets. Geomagnetically induced currents drive corrosion risk by shifting the potential of long pipelines. Operators monitor pipe-to-soil potentials and can temporarily adjust cathodic protection systems during strong events. Polar and high-latitude routes experience degraded high-frequency radio communication, and during strong solar proton events, elevated radiation concerns at cruising altitudes on polar paths. Operational advisories and route adjustments are issued when thresholds are exceeded. For most geomagnetic storms without major solar proton events, the main hazard is communication reliability, especially at night on transpolar tracks. Increased atmospheric drag at low Earth orbit raises decay rates and alters conjunction predictions. During active periods, operators raise perigee margins, switch to safe mode attitudes, and adjust thermal and power budgets. Strong geomagnetic storms can cause anomalies through surface charging and single-event upsets. Large satellite constellations face increased drag management workload during days with elevated thermospheric density. Precise positioning and timing degrade during strong geomagnetic activity. Dual-frequency receivers mitigate ionospheric delay, but can still suffer cycle slips, loss of lock, and solution convergence delays. Survey-grade accuracy in the decimeter range can be significantly degraded during peak storm intervals. Aviation integrity monitoring and maritime systems factor space weather into performance notices during large events. The outsized auroras of last year were driven by an unusually geoeffective sequence of coronal mass ejections from a very large active region, and they set a useful reference for comparing tonight's risks. On May 10 through May 13, 2024, a series of coronal mass ejections from active region 3664 produced the most intense geomagnetic storm since the early 2000s. The geomagnetic K-index reached 9. The disturbance storm time index bottomed near -412 nanotesla, and auroras were reported at very low geographic latitudes, including the Florida Keys in North America and across much of Europe and Asia. This event provides a high reference band for auroral boundary movement and for the type of sky brightness that overwhelms moonlight and light pollution. On March 13 through March 14, 1989, a storm with a disturbance storm time index near -589 nanotesla caused significant power system impacts in North America. The auroral boundary moved far equatorward into the middle latitudes. This event provides the critical infrastructure comparison for geomagnetically induced current risk. On October 29 through October 30, 2003, intense storms produced extreme auroras and significant satellite and navigation system effects. The disturbance storm time index reached approximately -383 nanotesla on October 29 and approximately -422 nanotesla on November 20. These events show that repeated strong storms can occur over several days as the same active region rotates across the solar disk. On May 13 through May 15, 1921, a historical superstorm is estimated to have reached a disturbance storm time index near -900 nanotesla, with widespread telegraph impacts and auroras far into the subtropics. This event defines the upper extreme for modern planning benchmarks. Risk bands for the next 48 hours are lower than the May 2024 maximum because the forecast notes low flare activity and uncertainty in southward magnetic fields within the incoming ejecta. Nevertheless, the combination of a shock, a sheath with intermittent southward intervals, and a following high-speed stream can produce periods of strong substorms and middle-latitude visibility if the north-south component turns south long enough. Convert uncertainty into checkpoints you can test yourself in real time using public data. Shock arrival. Look for a simultaneous jump in solar wind speed, density, and total magnetic field, followed within minutes by a step change in high-latitude ground magnetometers. If no shock arrives by the end of October 27th Universal Coordinated Time, lower expectations for widespread auroral visibility from this specific ejecta. Southward field persistence. After the shock, monitor the north-south magnetic field. If it turns south stronger than 10 nanotesla for longer than 30 minutes, expect rapid growth in the auroral electrojet index and visible auroras across the middle latitudes after local magnetic midnight. If it remains northward, confine expectations to high latitudes. Sheath versus cloud. If the strongest southward intervals occur within the first 6 hours after shock arrival and fluctuate rapidly, you are inside the sheath. Expect bursts of activity and uneven visibility. If a smooth rotation sets in with sustained southward values and declining density, you are inside a magnetic cloud. Expect more predictable storm development and longer observing windows. High-speed stream stacking. On October 28th Universal Coordinated Time, the predicted high-speed stream can reinvigorate activity. If speed climbs above 600 km per second with moderate southward intervals, Additional substorms are likely even if the coronal mass ejection underperforms. Ground truth. Combine global auroral oval nowcasts with auroral electrojet index plots and regional magnetometer arrays. If the auroral electrojet index surges and mid-latitude magnetometers show large deviations while your sky remains dark and clear, step outside. The arc may already be visible low on the horizon. Limitations. Ground cloud cover and urban lighting can prevent visibility even when geomagnetic conditions are strong. Forecast models for arrival time carry several hours of uncertainty, and the magnetic polarity within ejecta cannot be forecast with confidence before in-situ sampling at the upstream monitor. Subscribe and leave a comment with your city, latitude, and the time you observed auroral activity. Share whether the forecast checkpoints matched your sky.